In this lecture, we're going to look at several issues and techniques to optimize networks. So both in the sense of training, running the optimization, and also things that we can do to the neural networks and the loss function that help us get better results. So I'm going to start by giving an overview of some optimizers that we have available in TensorFlow and Keras, and look a bit at how to choose the best learning rate. Then I'm going to detail a bit more that issue of initializing the weights of our networks. We saw that we have to take some care with that, otherwise we can have the convergence problems, and you experimented with that a bit in previous exercises. So we'll look at some initializers that we have available in TensorFlow to help solve this problem. And then we're going to take a look at the problem of overfitting. When we are using neural networks for supervised learning, we want to minimize the error outside the training set. This may not always correspond to minimizing the error inside the training set because of the possibility of overfitting. The network learns too well to classify or to make predictions using the training set, and this makes it lose accuracy outside the training set. So we'll see review this bias variance trade-off to understand some methods that we can use in neural networks to minimize the overfitting problem, and then we'll look at regularization methods in neural networks. So let's start with the optimizers. A detailed look at the numerical optimization techniques that we'll be using in TensorFlow is outside the scope of this course. So I don't want to give you a too detailed look at these techniques. But we always will have this problem. We want to minimize some loss function. We are going to use the gradient information of the loss function using the automatic differentiation method that we saw previously. But then there is the question of how to apply this gradient information to change our weights. And that is the task of the optimizer, and there are different techniques for doing that. So one of the optimizers we already saw so far is this stochastic gradient descent. So let's say the vanilla version, where we take the gradient of the loss function with respect to each of the parameters we are trying to adjust, and we adjust the parameter by multiplying the negative of the gradient because we want to slide down the loss function, and we multiply that by a small value. This is the learning rate. So in this case, we have the same learning rate during the optimization and for all the different parameters. This is the basic version that we use. We can also use momentum, as we saw previously, where we use the gradient information to change the rate at which we are changing the parameter. So a sort of velocity, and we use the gradient to give us the acceleration. And this is a good idea. So if you use the SGD class, the stochastic gradient descent, this basic optimizer, you should use momentum because it gives you a lot better results. So we already saw this one, and this one is fairly simple. But one problem with this optimizer. So I think the sound is low. I can increase it a bit, but then there may be some noise. Okay, so let's try it this way. So one problem with this optimizer is that it uses the same learning rate for all the different parameters, and this may not be a good idea because the loss function may be more dependent on some parameters than others, and then because the gradient of the loss function, and so we may have less information about some parameters than others, and this can cause learning not to be as efficient. So one way of changing this a bit is using this adaptive gradient optimizer, AdaGrad, that keeps adding the gradients for each parameter. So this is the sum of the squared gradients, so that it's always positive. And then for each parameter, it divides the learning rate by this sum over the gradients, the past gradients for that particular parameter. This means that parameters that have smaller gradients will tend to have larger learning rates, and so they will not slow down as much during training. Also, since Adagrad keeps adding these squared previous gradients, then this number keeps growing during the optimization, which means since it's dividing by that number when computing the updates, the learning rates will slowly shrink during training, and this is good for convex problems. Basically, convex problems are those where we have a well-defined minimum in some value, in some hole in our loss function, and we want to slide down and find that minimum. So since the valley grows narrow and narrower as we approach the minimum, it's good to slow down the learning rate so that we don't overshoot and lose convergence. So adaptive gradient is a bit more sophisticated than the other one, and basically keeps track of all the previous gradients, adds all that information, all those values, and divides the learning rate for each parameter by the sum of the previous gradients. So that parameters with large gradients will not overshoot, will not take too large steps, and those that have small gradients will be moved a bit faster so that they don't bog down all the training. With RMS prop, it's a bit different because instead of adding the squared gradients over all the history of the training process, it keeps a moving average, a moving mean of the squared gradients. Actually, it's the root of the mean of the squared gradients, and that's why it's called RMS. And it will divide each gradient by this moving RMS when computing the update. So this will not shrink the learning rate over the training because it's keeping a moving average, and it will tend to make the update similar for all parameters since it's dividing by this moving average of the gradients over the last iteration. And this means that it solves this problem of some parameters changing very slowly because they have very low gradients, since in this case with RMS prop, everything is moving, is changing approximately at the same rate. And this is good for non-convex problems, so it's often used in recurrent neural networks. So there's a bit of a problem with the audio. I'll see, I can increase the sensitivity here a bit, but I'll try not to put this too much because of the eventually it will start getting too noisy. But I'll see if I can test this during the break and see if I can solve it. Okay. So moving on, this, by the way, RMS prop is the most widely used optimizer that was never published. This was first introduced in a course, and it was never published by the authors, but it's widely used, and you find it implemented in Keras too. Adaptive moment estimation. This ADAM brings together these different tricks, so to speak, these different techniques. So not only uses adaptive gradients by using this moving average, in this case this is an exponentially decaying average, but also uses momentum to further improve the speed of the learning process. So Adam tends to be the fastest optimizer, and you can experiment with Adam. But by using all of these things all at once, sometimes it has convergence problems. So sometimes it's hard to fine-tune Adam to adjust the learning rate to get it to solve, to converge adequately in training our network. So there is no real way of trying to predict in advance what would be best. In general, there are some rules that you can follow. For example, RMS prop seems to be the best one often in recurrent neural networks and some specific applications like that. But I would say the best thing is to experiment a bit first to choose the best optimizer. So you could start, for example, with Adam, and if you find you have problems with convergence, then choose a different one. And the basic stochastic gradient descent is probably the safest one, although it will tend to be the slowest one often. So another thing we need to do is to choose the learning rate. You already experimented a bit with this, and I think you saw that if you use a learning rate that is too high, then you can have problems with convergence. You can have things oscillating a bit or even very much. For example, you can have those errors of not a number appearing if you use a learning rate that is too high. So one thing that you can do is experiment by changing the learning rate and look at the plot of your loss function. In general, if you see some oscillations in the validation loss, for example here, this that we can see in green, this often happens because as we are changing the parameters to minimize the loss in the training set, sometimes this doesn't help very much in the validation set. But if you see many oscillations in the training set, this is a clear sign that your training rate is too high and you're failing to converge. So if this happens, you should reduce the learning rate to avoid this problem, because this will prevent you from finding a good solution, since it will keep oscillating and not converge well. Of course, if the learning rate is too small, then you'll see that it takes too long to go down the loss function. So you should not use a learning rate that is too small, otherwise in practice you will not be able to train. So one thing you can do is to use a small subset of your training set, say a few hundred examples. This way you can run many epochs and you can see the loss function going down fairly quickly, because your network is just adapting to a small set of examples. Of course, in this case, you'll have a lot of overfitting, but you don't need to worry about that, just to adjust the learning rate. And you can run a few experiments just to see how high you can put your learning rate while avoiding those kinds of oscillations, those convergence problems that you have here. You can play it safe and then use a learning rate that is a bit lower than that, but this would be one quick way of trying to find good values for your learning rate. Of course, you can also schedule decreases in the learning rate over training. So you start with a higher value and then it will go down gradually towards convergence. Fine-tuning that process, it's a bit more laborious and you need to experiment a bit. But in any case, the important message here is that you should run a few training runs, for example, with a small subset of your training set, just to have an idea of what a good learning rate could be, so that you avoid either having to wait a very long time for training your network or convergence problems if your training rate is too high. Another issue that we saw is the selection of the initial values. So basically the bias values, we can just simply start them at 0. But the weights need to be randomized or different between different neurons. Otherwise, we'll have identical neurons in the network, and these will always change in step. So we need to break this symmetry in order to use the full network. And we experimented with a normal distribution, starting initializing the neurons like that. But then we saw that if we have too many neurons in the layer, this will add up all of those values, and we have numerical instability soon because of the very large values in those sums. And what we did was a simple trick of dividing by the number of neurons. So there are other more sophisticated methods. This LeCun normal initializer uses a normal distribution for the weights, but it has a standard deviation that is the square root of 1 over the number of inputs into the neuron. So we are calibrating by the number of values that are coming into the neuron. This Glorot uniform it's called Glorot uniform in Keras. This is normalized initialization, and I think this one is the default currently. Uses both the inputs and the outputs of the neuron. So fan in are the inputs to the neuron, fan out are those neurons that will receive the output of this neuron in the next layer. And it uses a uniform distribution ranging from minus this 6 over square root of 6 over the sum of these fans and plus that value. So this, I think, is the default currently, and it calibrates the initialization of the weights according to how many inputs and how many outputs are involved in each particular neuron. And this allows us to avoid those problems of instability if we have a higher learning rate and high values in the weights. Because remember that all of these things are multiplied. So if you have a higher value on one of them, you need to have very low on the other. So it's good to have some kind of standardized range here, so that we always have a general idea of what the good values to try would be. Another thing that can help training a lot is batch normalization. So we already saw that standardizing the inputs is a good idea for neural networks, instead of starting with a very large range of values and expecting the network to adapt to them. We can standardize and keep everything close to zero with a standard deviation of 1, and this will make it so that our training always uses similar ranges of values. So we also have a general idea of how to initialize the network and how to calibrate the learning rate, because these three parameters, these three values, will end up being multiplied during training. The input is multiplied by the weights, and then the weights are multiplied by the training rate. The gradients with respect to the weights are multiplied by the training rate. So if the magnitude of these values is too high, we need to adjust the others to compensate. But if we always standardize the inputs and we always use this kind of initialization, then the learning rate will always be around the same kinds of values, same range of values, and we have an idea from the start of where things should work. So this is something that we do in the inputs, but we can also do between layers in the network. And that's the idea of batch normalization. What we're going to try to do is to use standardization. So it's called batch normalization, but we saw that in a different context we use normalization to refer to the rescaling methods that changes everything to a scale between 0 and 1, and standardization to the rescaling methods that shifts the mean to 0 and the standard deviation to 1. So actually batch normalization is more accurately a standardization and not a normalization. But the idea is the same that we are applying when we standardize the inputs to the network. So we want to give to the network a set of data that has a mean of 0 and a standard deviation of 1 for all the features. And this helps the network because it always starts with a cloud with that same shape. But if we are training the network, then the output of the first layer will not necessarily have a mean of 0 and a standard deviation of 1, because we start with random weights and then we start to optimize them using the gradients and so on, and this can give a very different result. Batch normalization works by taking a running average of the batches that we are supplying to the network during training. And it takes the running average of the outputs of this previous layer and also computes the standard deviation. And it will apply those values, average and standard deviation, to rescale the output of this layer before inserting it as an input to the following layer. So it's basically looking at the data as we are training the network, taking a running average over all the data and using that information to standardize the inputs into the following layer. So, this way we are standardizing the outputs of one layer, and the next layer will not have the additional work of trying to deal with large changes in the mean values and in the standard deviation of the outputs of the previous layer. And this can be included in the auto differentiation, the automatic differentiation, since these rescaling operations are just subtracting the mean and dividing by that standard deviation. So these work here as constants as far as the automatic differentiation is concerned, because these are not parameters that are being learned by the optimizer. They are parameters that are being adjusted just by computing the outputs of the previous layer over the previous batches, keeping this running average. So in Keras you can do this easily, as we'll see in the second lecture after the break, by just adding a batch normalization layer. So this will receive the inputs of the previous layer, rescale them using these running averages, and then feed them into the next layer. And this is how it works during training. When we are training the network, the parameters of the batch normalization step keep updating by computing these running averages of the mean and standard deviation of the outputs of the previous layer. However, when we stop training, then these parameters are fixed. They are the result of averaging over the whole training set and keeping these moving averages. And then we will be using those parameters in prediction afterwards. So this is how it's implemented in Keras. And this has the effect of speeding up training quite a lot, because it simplifies the tasks for each layer, because it keeps standardizing the inputs for that layer. So the layers don't have the additional work necessary to keep dealing with changes in the mean and the variation of the inputs from the previous layer. Okay, so these were issues about speeding up training, making training faster. Now we also need to make the training better. One problem here is overfitting. What we want to do with supervised learning when we are training these kinds of networks to do some prediction is to have an accurate prediction outside the training set. The training set is already labeled. We don't need to have a good prediction because those labels we already know. What we want the network to do is give us a good prediction outside the training set. So the problem here is this problem of overfitting. We saw this in machine learning last semester. Basically, if we have a model that can adjust too much to the training data, then it will start learning things that don't generalize outside the training set, and it starts making more mistakes for future data, which is what we want to avoid. So two ways basically of solving this is one, selecting the right model, so adjusting the power of the model to fit the data, and thus minimize overfitting in that way. So this is model selection, and you can do this easily in neural networks by adding more layers, subtracting layers, changing the number of neurons, things like that, because with neural networks you have a very versatile architecture that you can fine-tune. So this is one way of solving this problem, creating a network with the appropriate architecture and the number of layers and neurons for the particular problem you're trying to solve. Another way of doing this is to adjust how the network is trained. And this is called regularization. We are not changing the model. We are just adjusting the way we are fitting the parameters in order to minimize overfitting. So we're going to look at this approach in a bit more detail. The way to check for overfitting is basically to use some set of data that is not being used to optimize the parameters, so it's outside the training set, but that you can look at in order to optimize these other decisions. the kind of model that you're using, how much regularization to use, and so on. So one thing we can do is cross-validation. We saw this in machine learning, and the idea is that we have our training set. We leave some subset of these examples outside, and we train with only the remainder. Basically, we are using k-folds cross-validation, so we split the training set into k partitions, these k-folds, and at each iteration we leave one of these groups out, we train with the rest, and we compute the error in the set of points that were left out, the validation set for this iteration. But now we repeat this by leaving another subset out, another and another, and then average over all these iterations to get the cross-validation error. So this is a good thing to do when we have models that are trained very quickly, because then we run through all of these iterations and get a good estimate of what would be the error outside the training set under these conditions with this kind of data, model, and the way it's trained. But it's generally not very good for deep learning, because with deep learning, with cross-validation, will generally take a very long time. If you have to train the network and it takes, for example, 3 or 4 days to train your network, if you want to do that 5 times, then you are talking about 2 weeks just to do cross-validation. So generally, it's too costly to do cross-validation in deep learning. On the other hand, cross-validation is good when you have not very large data sets, so when data is a bit scarcer, since it helps you get a better estimate of the error outside the training set, even when you don't have many data points. But this is not a problem typically in deep learning. In general, we are going to apply deep learning when we have very large data sets. So in general, cross-validation is very widely used in classical machine learning, where you can train your models very quickly and you don't have huge data sets, but it's not as used in deep learning because you have the reverse situation. You have a lot of data typically, and your models take a long time to train. So in deep learning, what we will generally use is this approach of using a validation set. So you can imagine that we are just doing this once. We have a set of points for validation, a set of points for training, and we look at how training is going in the training set and the validation set. So this way we can estimate how well our model is being trained and how serious is the overfitting problem in each particular case. Then there is an additional problem here, which is getting an estimate of the true error. So even after all this fine-tuning, and we train our model and we have the final hypothesis, so our network fully trained with all the parameters instanced, we may want to have an estimate of what the error will be when we apply this network to make predictions in the future. So the true error will be the average error over all the possible data, all the examples we are going to meet in the future, but we obviously cannot measure this because we don't have all possible data. We just have the sample that we are using. So we have to estimate this with a test set that not only is outside the training set, because the training set, the training error is biased by the process of optimizing the parameters in order to minimize the loss function using that training set. But we cannot use the validation set either, because we've been using the validation set to fine-tune the architecture, to fine-tune the regularization parameters and things like that. So the error we are measuring on the validation set is also biased. What we have to do is, at the beginning, if we want an unbiased estimate of the true error, at the beginning we need to set aside a subset of examples just for estimating the true error at the end. So this will not be used to make any decisions, to optimize anything. It will only be used to obtain this estimate. And that means it's an unbiased estimate. It can be above or below the true error because it's just an estimate, but at least it will not be biased to any side. So this will be the general procedure. When you have your data set, you set aside a subset of examples for testing at the end, and then the remainder you split into training and validation so that you can optimize your network and everything that you need until you get the best possible result on the validation set. After you do that and you have your network trained, you test it on the test set and you get an estimate of what the error will be in the future. Okay, so if the model is adapting too much to the data, so it's overfitting, you can find this when you plot the training and validation losses, and you see this large difference between training and validation. So in this case, this would be the miles per gallon problem that you solved in the exercise, but using a very large network. This one has 100 layers, 100 neurons in the first layer, then 50, 10, and then 1 in the output layer. And you can see this network has so many parameters, and it's so it can adapt so well to the data that it really shrinks the loss function. So this is the mean quadratic error in miles per gallon, the root of the mean quadratic error. So it's in miles per gallon, and we can see that is giving us a very accurate prediction of the miles per gallon for each car in the training set. However, the error in the validation set is much higher. This means that this network is adjusting too much to the training set, and it's not working very well for the cases that interest us, which are those that are outside the training set. You can have a network that is working better if you see that training and validation are not very different. So this means this particular network, 30, 10, 1, does not seem to be overfitting and gives us a reasonable accuracy. Note that the error now on the training set is higher, so we had to reduce a bit the power of the network and the ability to adjust to the training set. But the error on the validation set, which is the one that really matters when we apply the network to make predictions, is now much lower than it was previously. So this is a better network than the other one if we want to predict the miles per gallon in future examples outside the training set. Of course, you also need to take a bit care to avoid underfitting. The underfitting problem is when the network or the model in general is too simple and cannot adjust adequately to the data. So this would be an example of a network with 3 neurons, 2 and 1. This is too simple for solving this problem. We can see that training and validation error are the same, but the loss function stops decreasing right here at the beginning after a few epochs, and it doesn't change any much further. So this means that the network was adjusted as well as possible. There is no generalization error. It's not overfitting our data, but it's clearly underfitting because the performance overall is much worse than it could be with a more complex model. So this is the general problem when you're trying to select how to build your network, what the architecture should be. You should try to minimize the validation error. And you do that by avoiding very complex models or very powerful models that will overfit and give you a large validation error. But you must also avoid excessively simple models that cannot even adjust to the data. And even though they don't have overfitting, you have a large error because they are underfitting in this case. Okay, so let's look a bit at the theory behind this, and these are concepts that are also important to understand some regularization techniques, bias and variance. We can think of the error that our network is making as being the result of adding these two terms. The bias is the deviation between what the prediction should be and what on average instances that we are creating by training our model will give us when we train with that training data. So we say that our model is biased when whenever we train our model, we tend to get predictions that are, for example, biased to be larger than what they should be, or smaller, something like that. So bias is this difference between the average prediction of networks trained from this architecture, for example, so hypotheses obtained from the model when we train them with this kind of data. And variance is how spread out these predictions will be when we train our model with different samples of data drawn from whatever the universe is giving us. So to illustrate this graphically, we're not going to lose much time with the formula, so we don't need to look at this in that detail, but basically the bias is this average difference between the average prediction of our model for each point and what the target should be, so what the prediction should be. We can compute the square of this difference and then average it over all the data, and this gives us a measure of the bias for our model. The bias for a single point is simply the square of the difference between the average predictions and the target value. So we can imagine here that these lines represent hypotheses, instances of some model that was trained on different samples of these data. So by using different training samples, we get slightly different results in the end when we instantiate all the parameters. If we average all the predictions for this value here, we see that our model is biased because every time we train it, it's going to do a prediction that is above the real value. So on average, it's going to have this distance here, this difference between the prediction and the real value, and this will be the bias on this point. Bias tends to be high when we are underfitting. We can see here that for this, the shape of this data, using models that do these kinds of curves are too stiff for to accompany the shape of the data. So they tend to have this bias. They tend to overestimate on this region and underestimate on this region, and cannot fit the data properly. So this is one source of error when we are trying to make predictions, is if our model does not fit the data well, it will be biased in different regions, in different parts, and this will increase the error of our predictions. The variance is it's literally the variance of the predictions on each point. So basically, it's how spread out the predictions are. And this tends to be more serious when we are overfitting. So basically what we're doing is for each point, we are computing the variance of our predictions, which is the average of the predictions minus each prediction and the difference squared. And when we average this, we get the variance for the predictions around for one point. So the dispersion here will give us the variance at this point. And if we do this for all the data points and average out for all the data points, we have the variance for our model. Again, these lines are different instances of our model obtained by training on different samples of the possible data. So this is more a theoretical concept. We are not going to actually do this. We're not going to train hundreds of neural networks just to measure the variance. But we can see that there are two different sources of error here. When our model does not fit the data too well, it will have a bias in that region. And this we cannot really fix without changing the model, because there is no way that we can solve this problem unless we, say, use combinations of different instances, or we use a more complex model, something like that. But reducing variance is much simpler if we just do some tricks, like, for example, averaging over the results of different instances of the model will tend to move us closer to the mean point here. Or if we prevent the model from giving us so many different solutions, and we constrain a bit how we train the parameters, we can shrink down this spread and reduce the variance. So typically, what we can do is, if we notice that our model is overfitting, we can try to use some additional techniques that reduce variance and thus reduce the overall error that we're getting in our model. And this basically we can do by selecting different models, and if we do that, we have this bias variance trade-off. This is a trade-off because if we use a very simple model, let's consider that simpler models are on this side, for example, simpler networks, something like that, and more powerful models are here to the right. Then if we use a very simple model, as we saw in the miles per gallon example, we will have a large bias. The variance will be small, but the bias will be large, and so the overall error will be large. As we increase the power of the model, we start decreasing bias, but eventually we start increasing variance. So if we go too far, we'll also have overfitting. We start having more error by starting to overfit. So we cannot really go too far to either side. And we need to optimize this trade-off between bias and variance by choosing a model here in the right place. So this is basically the idea when you're trying to find that sweet spot on the complexity of your model to solve a particular problem. Another thing that we can do when the model has a high variance is to try to prevent it from adjusting too much to the data. So basically, when the model has a high bias, it's underfitting. The variance tends to be low because the model will always get stuck on the same kind of solutions, but we have a high error outside the training set because the model cannot adjust properly. We also have a large error inside the training set, so this is one easy way of diagnosing underfitting, if the error is large both in training and in validation, for example. There are some ways of solving this, for example, boosting. We saw this with in machine learning, but this is usually not a problem with deep learning because we can always add more layers, increase the number of neurons and so on. So it's relatively easy to solve underfitting with deep learning because we can add complexity to the model. High variance is, however, a larger problem in deep learning because we tend to have models that are very powerful, have too many parameters, and can adjust too much to irrelevant data. So this is something that is common in deep learning and can be fixed either by changing the network, or often it's better just to use regularization. So regularization is a change to how the model is trained, not a change to the model itself, but some change to the way the model is trained that will reduce overfitting. In general, it's going to reduce variance. It may increase bias a bit, but it still compensates by reducing the variance of a model that is in overfitting, and that makes the error lower outside the training set. So one possible way of doing this is adding a term to the loss function that will penalize the parameters being too large or having too many parameters. Now it depends on what the term is. And this would be, we have here our original loss function, for example, the quadratic error or those cross entropy loss functions that we saw. And we create a new loss function that adds a small fraction of this function of the parameters. So generally, this function of the parameters is one of these two. In L2 regularization, this is simply the square of the size of the parameter vector. So basically, we are adding the square of all the parameters, and we are adding a small fraction of that as a penalty. So in L2 regularization, we are penalizing the overall magnitude of our parameters, and especially the very large parameters, so because this is squared, so we tend to shrink the largest parameters and find a solution that prefers to have small values for all the weights of the network. In general, we do not include the biases here. So we are just penalizing the size of the weights, those values that are multiplied by the inputs, and not the bias values for the neurons, which just serve to shift the activation function. So those we don't include them in this penalization, because that would be constraining some parameters of the network that we should not constrain. We should let them adjust freely. Another form of regularization is L1 and penalizes the sum of the absolute values of the parameters. So this omega function here is the sum of the modulus of the parameters. And these have different effects. L2 regularization is also called weight decay, because when you compute the derivative of the loss function, you have the derivative of the original loss function, whatever it was. And then, since this is the square of the parameters, the sum of the squares of the parameters, when you compute the derivative of this with respect to one particular parameter, particular weight w, you just have 2, which comes from the square there, times this alpha and the weight. So the update rule for the parameter, since we are sliding down the whole cost function, is just to subtract from each weight, in addition to the information coming from the gradient, we also subtract a fraction of the weight. And this makes the weight decay, because if the weight is not contributing to the gradient, let's suppose that this is 0 and that particular parameter is irrelevant, the parameter will tend to shrink over time during training. So L2 regularization in neural networks is also called weight decay, because it tends to shrink those weights that are not contributing to minimizing the loss function. In L1 regularization, we are penalizing the models or the module of the weight. So basically, we are adding or subtracting a constant that depends on the sign of the weight. So it will be negative for negative weights, positive for positive weights, and we are subtracting that from the weight. So since it's going to penalize parameters by a constant value when we are doing the update, it's going to update them by adding this constant value. This is going to tend to lead to a sparse network where a subset of the weights will have an optimal value of 0. And so the big difference between L1 and L2 regularization is basically that L1 regularization is reducing variance. It's minimizing the spread of our hypothesis by minimizing the number of weights that are not 0. Everything that is not very useful for solving the problem will tend to go down to 0 and be disconnected, so to speak. L2 regularization will minimize the overall magnitude of the weight. So basically it penalizes more those weights that are larger and tries to shrink those. So we will have all the weights generally non-zero, but they will tend to be smaller than they would be. So these are two forms of trying to reduce variance and thus reduce overfitting by changing the way the network is training. And that's why it's called regularization. But we can also change the way the network is trained without actually changing the loss function like we did here. For example, one way of improving training and reducing overfitting is to use data augmentation. It's easy to see that if we have more data, we will have smaller problems with overfitting, because now the network will tend not to learn things that do not generalize. Of course, having more data is not something that we can simply choose to have, because either we have data or not. But in some cases, we can generate additional examples by doing some sort of transformation that we know could occur in practice. For instance, suppose that we have this example in our data set and we are training a network for facial recognition. We could rotate the face, do some slight deformations, for example like this, shift the image to one side, mirror the image and so on, and all of these would still be examples of faces. So we could, from one example, generate a set of different examples and in practice increase the size of our data set by augmenting it with these transformations. Note that this does not work for any possible problem. In this case, it's easy because a face is still a face even if it rotates or shifts or something like that. But for example, if you are doing character recognition, you cannot rotate a character. If you rotate a P, for example, you can end up with a D or something like that. So you cannot do these kinds of operation in general in all data sets. But there are some data sets where very naturally you can find transformations that help you increase the effective size of your data set. And this can even be done inline during training. So when you're creating your mini batch, you can add some examples from the training set and some augmented examples generated at that time if you don't want to store everything on the hard drive, for example. Another way of doing dataset augmentation, and this is done implicitly, is by noise injection. So imagine that each time you present an example, you add a small amount of noise to the input. You have those features, but you change the features slightly by adding, for example, normally distributed noise with some small variance or something like that. And this will, in fact, make all the examples you are presenting the network slightly different, because it will never see exactly the same thing twice, and this will increase in practice the data that you are giving the network. Of course, this has to be done carefully, because if noise is too much, then you start misleading the network, because you'll have an example classified with some particular class, but by the noise that you changed, it should be in a different class or something like that. So we must be careful with this, but we can use this, and in Keras you have these layers that you can add to add noise automatically. You can also consider the output to be noisy. There may be actually errors in labeling the data, so the labels may not be perfect, and so you can once in a while change, for example, the class label of some example at random, or you can use label smoothing instead of having labels. For example, for a binary classification, instead of having labels that are 0 and 1, you can have labels that are, for instance, 0.1 and 0.9, so that your network doesn't try to be absolutely sure about the class of each example by trying to approximate 0 or 1 in the estimated probability of belonging to a class, but it's more conservative and tends to go to slightly lower or more uncertain values. So noise basically is a way that we can use both to augment data implicitly by injecting it into the features, and also to take into account some uncertainty in the labels, or not forcing the network to try to adjust too much and make too strong a prediction by smoothing the output. So all of these things will change the way the network is training without changing the network itself, the architecture, how the model is. So all of these are forms of regularization, and they aim at reducing overfitting, basically. Another thing we can do is early stopping. Our network is learning gradually, adjusting to the training data. If we let it run too long, it can start overfitting very much, and it will perform worse than if we stop training early and don't let it overfit so much. So this is not a particularly good example. It's just one of the runs that I got, but you can see here that validation error goes down and then goes up again. The validation error is considerably higher than the training error, although the scale here is different than from the previous chart. So this model is a bit overfitting. Maybe it's not a very good one, but you can see that it's even worse if we let it train more epochs, because it starts to adjust too much to the training set and the validation error keeps increasing. So one form of regularization would be to stop training here where validation error is at its lowest point. And you can easily do this by saving the weights whenever you find a lower value for validation. And then when you reach the conclusion that things are getting worse, you just stop training and load the weights that were saved at that checkpoint. So Keras can also do this automatically, and so this way it's easy to find the best spot to stop training so that you get the best results outside the training set. This is also a form of regularization because, again, it doesn't change the network that you're using, but it changes the way it's being trained. You are aiming at stopping it where it minimizes the validation error. Another thing that we can use when we have models that are overfitting, the model is overfitting because it has a large variance. And so if we average different predictions of different instances of that model, so different hypotheses, we can improve prediction by reducing variance without compromising bias. So the model can still adjust well to the data, but we are averaging over a large number of predictions. And this we saw last semester as bagging. For example, we use bootstrap aggregation to train many instances of the model, and then we average or compute the median of the predictions. With deep neural networks, this is not very practical. You're not going to train 500 instances of the network because that would take too long and would take up a huge amount of space, and then run those predictions and so on. That would be computationally very demanding. But there is one way of implicitly training a large number of networks with only one single network, and this is called dropout. So this is a regularization technique in deep learning that is conceptually analogous to bagging. In bagging, we explicitly train different models. In dropout, what we are doing is, during training, we are randomly switching off some of the neurons in each layer. So this works best with dense layers. And in this case, we have a dropout probability on each of this layer, which means that for each mini batch, there is a probability that some neurons will be as if they are not in the network, will be simply switched off. So you can see that at each mini batch, we are actually training a sub-network created by the combinations of neurons that are still turned on. And so in another mini batch, we have a different subnetwork and a different one and so on. And at the end, we have, in fact, as if we were training a very large number of networks, and we are averaging their predictions because in the end, once we finish training, we turn on all the neurons and we calibrate the output so that the average output is the same as it was during training. So basically, dropout is this technique that by switching off neurons at random during training will give us the equivalent of training a large set of models. So during training, we are turning off neurons at random. After training, we scale all the outputs of the neurons by the probability of being on. So, for example, if you use 50% dropout probability, then on average, each neuron is only active 1/2 of the time on the mini batches during training. And so after training, we scale down the outputs of the neuron by 1/2. And this means that the average output of the neuron will now be the same during prediction, during inference, as it was during training. So this is the general approach to dropout, and it's the way it's implemented in Keras. There is also a variant, inverted dropout, which instead of adjusting the weights after training, the activation is increased during training. So if you use a dropout of 0.5, then the activation is multiplied by 2 during training so that it's calibrated to compensate for the fact that half of the time the neuron is switched off. But in any case, this is the more useful, the more usual implementation, just rescaling everything at the end. And the important thing to remember is that when you are using dropout, there will be a rescaling after training to compensate for the times the neurons were disconnected. Another thing that we can use to improve results is to use adversarial training. There are some strange mistakes that an artificial neural network can do. For example, if we presented this image to the trained network, it will tell us that the most likely class is Panda with 57%. If we generate this image at random, or if we generate this image, it's not quite random, it will tell us that it's most likely a nematode, but with only 8%. So clearly the network doesn't know what this is, and it's just taking a wild guess, but it doesn't have much confidence. But if we add a very small fraction of this image to that one and ask the network to classify the result, and the result is this one, we don't even notice the difference because this is only 7 parts in 1000 of this one added to that one. But now the network tells us that this is a given with 99% confidence. And the reason for this is that this image was generated by looking at the sign of the gradient of the loss function with the trained network as a function of each of the pixels. So we are choosing the pixel values that maximize the change in the loss function. And this will make the network now, it will basically use all the weights of the network to find out how to give the largest change to the prediction of the class on the output. And so even this small change will deceive the network. There is some research on doing these kinds of things to actually deceive neural networks and classifiers, but for our particular case here in improving training, this is called adversarial training, which is to add these kinds of examples to our data. So they are generated by looking at for a particular set of weights that the network has, which is the best way of deceiving the network, and then adding these examples to the training network and to the training data, and keep training the network so that it becomes more robust to these kinds of problems. So basically what we are doing is making the network be less sensitive to these small changes in the input by being more locally constant on the neighborhood of the training data. So the gradient of the loss function will be lower in the neighborhood of the training data, and the network now does not respond so easily to very small changes in the examples. And now we also have the problem when we are trying to optimize our networks of how we can select all these parameters. The size of the network, the architecture, the regularization methods, and so on. So now here we have different strategies. One is the simplest one, you just experiment with a few combinations. You can also do some automated search, like a grid search, a random search, or something like that. This can take quite a while if you do it with the whole data set, but for some things, maybe you can experiment with parts, with just a fraction of the data to see how it works. But in general, for actually optimizing these kinds of parameters in order to improve the result of the networks, you should use all the data that you're going to use for training. So basically this tends to take a long time, and the way you're going to search for all these combinations will depend on how much time you want to spend optimizing the network. So this will be a kind of a meta problem. You have so many different options and you probably cannot test all the different combinations. But if you experiment a bit, you can get some idea of which things work better or not on your particular problem. Okay, so to sum up this part, we looked at optimizing in general, the optimizers that are actually fitting the parameters of the network, and also optimizing the way the network will work. The speed of the training, so using the right learning rate, batch normalization also speeds up training, and optimizing the predictions of the network, selecting the appropriate model, and selecting regularization to try to overcome overfitting, which in the case of deep learning is the most common problem. We generally do not have problems with underfitting because that simply requires adding a few more layers or more neurons or something like that. So you can take a look at these chapters and sections of the deep learning book for more details on this. And we're going to take a short break, so let's start at 10:15. Okay, see you soon.